Hello everybody. In this video lecture, we will cover physiology of the nervous system. So I will use this PowerPoint video lecture, Physiology of the Nervous System, to help myself. So let's go ahead and begin. So we're going to start with principle of electricity. What you see on this picture is a battery. And you know your battery has potential energy. You can use battery, let's say, to make a light bulb work, or you can use battery to make your remote work. You can use battery to make your laptop work, right? So battery has potential energy. So how does battery has a potential energy? Because there is separation of positive and negative charges. So when we have separation of charges, this is called voltage, and this is electrical potential. So electrical potential is energy that can be used to do some work. So separation of opposite electrical charges called voltage or electrical potential. And if opposite charges are separated, the system has potential energy. So all you need to do, you need to connect negative and positive end. And when this happens, we have electrical current. Then charge particles, in these examples, electrons have negative charge. They start moving, right, from negative end to positive end, and this movement of electrical charges is called electrical current, right? So, well, that's a very brief introduction to electricity. So we separate charges, we store potential energy that is called voltage. And when we have movement of electrical charges, we have electrical current. Now, how it is relative to the cells and specifically to neurons? Well, actually, not just neurons, but all cells of your body, they establish this electrical potential. So there is separation of charges across a cell membrane. And this is called resting membrane potential, and it can be measured in voltage. So it's equals 70 to 90 millivolts. That makes sense. So if you look at a cell, so the cell would have separation of charges across a cell membrane. Right, and this is called resting membrane potential. Now, in this lecture, I will try to explain you why these charges are separated and how this potential energy can be used. Now, neuron function. So here we see neuron, right? Cell body, dendrites, and axon. And if you're looking at a part of the axon, so here we make this part bigger, you see there is a separation of charges, negative charges inside and positive charges outside. So this cell, it's like a little battery, right? Now, this separation minus and plus, this is resting membrane potential. Now, for a short period of time, we can have a switch of these charges. So a cell became positive inside and negative outside. And this is called depolarization. And why cell became positive inside? Because some positive particles start moving inside, negative particles start moving outside. And remember, when charged particle moves, that's electrical current, right? So that function of neuron to transmit this electrical impulse, right? So here's our charges goes, positive charges goes in, negative charges goes out, and this would create the movement of charged particles. So it's create electrical current that is called action potential over here. So neuron function is to conduct an impulse. So that's the impulse, and you see how it moves from one part to another. So it's propagating itself. And we have two types of conduction, normal or saltatory. Normal, it just continuously move along an axon, and saltatory when it jumps from one node of Ranvier to another node of Ranvier, right? So it will make more sense. I hope it will make more sense in a couple minutes. Now, excitable cells. Excitable cells are cells that are able to produce and respond to electrical signals. And excitable cells include neurons, muscle cells, skeletal, cardiac, and smooth, and some secretory cells, such as pituitary cells or insulin-producing cells of the pancreas. So the first, you need a separation of charge or electrochemical gradient that would give you potential energy. And several cell membrane proteins are needed to create the charge separation. So what are we doing over here? So our goal is to make a cell to look like a battery. So we want to separate positive charges and negative charges. And we want to keep negative charges inside a cell and positive charges outside a cell. If we can do it, we will create this potential energy, right? So that's what it says. So first, we need to separate the charges. Here are some proteins that are involved in separation of charges. Sodium, potassium pump, sodium and potassium leakage channels, sodium, potassium, and calcium voltage gated channels, or VGC, mechanically gated channels, and ligand gated channels. So all these channels are important in separation of charges across a cell membrane. So let's look at this picture here. So what shows here, extracellular fluid, intracellular fluid or cytosol, plasma membrane. And now we have a channel. This is leak channel or leakage channel that is always open. So ions can move in and out. Well, that's good, right? Because if something, let's say this is potassium, right? Let's say it's potassium plus. So if potassium can move, right, we have possibility to separate these charges. Let's see how this one involved in a minute. Another channel is ligand gated channel. But this channel is not open. This one is always open. This is not open. It's actually closed. So particles cannot move through this channel. How to open this channel? Well, some kind of molecule that is called ligand need to be attached to this channel. So the ligand is attached, and ligand can be, for example, neurotransmitter or hormone. So when this molecule attaches to this channel, the gate opens and ions can move, either in or out. That's why it's called ligand gated. So again, if charged particle can move, good, possibly we can separate charges. So we will see how this one involved as well. Now, voltage gated. Voltage gated are also closed. But to open this one, we don't use ligand, we use change in voltage. Look over here, we have negative charge inside and positive outside, and this channel is closed. But if cell became positive inside and negative outside, you see how we reverse this polarity, then this voltage gated channel open, allow particle to move through it. And the last type of channel, mechanically gated channel, again, it's closed. But if you have some mechanical deformation, let's say somebody touching your skin, this is mechanical deformation that can open this channel, and again, ions can move through it, right? So all these channels are involved in some degree in a separation of positive and negative charges across a cell membrane. Now we're gonna do overview first. Now your cells over here, right? Every single cell, including neurons and muscle cells, they are negative inside and positive outside, and we can measure this difference in charges, and it will give us minus 70 millivolts. So this is called resting membrane potential. Your cell is polar, right? Your cell is polar because your cell is negative inside, positive outside. Let me get a pen. So, okay, so here, look, let's imagine this is a cell, right? So here's the nucleus. Now, cell is negative inside and positive outside. We didn't discuss yet how these charges were separated, but just look at it this way. Cells are negative inside, positive outside. So we have separation of these charges, and in this lecture, I will explain you why. Now, if we have the separation of charges, do you think this cell is polar? Yeah, it is polar. It's polarized. It's polarized cell. It has positive and negative, so it is polarized. This separation of charges we can measure, and it gives us minus 70 millivolt. And this is called resting membrane potential. Now look what happened over here. The voltage became less and less negative, going towards zero, and then it became positive, right? So this area over here, so it would be if we have, okay, so we have less and less negative, and finally we will get positive inside, right? And negative outside. So this will be our plot 30. So if this is polarized cell, then this is depolarization, right? So this is called depolarization. And now look, inside the cell, it became negative again. So here's one part, right? This is this one. Cell is polarized. Now this, when we flip the charges, right? This is this part. This is called depolarization. Here's, by the way, the name, depolarization. Now over here, look, what's going on? We're going back to negative. So here again, negative inside, positive outside, right? This part. This, we back to polar state, right? So this is gonna be repolarization, repolarization. So here's the name. So this is repolarization number 3. And then back to the resting potential. Number 1 and number 4, if you look here, resting potential. So resting potential, cell is negative inside, positive outside. Depolarization, cell became positive inside, negative outside. And then repolarization, back to negative inside, positive outside, and then back to resting potential, minus 70, right? That's only overview. Now, here we're looking at the, here we're looking at part of the axon, and this is inside axon, and this is outside. Now, if we have the same concentration of sodium, potassium inside and outside, so here we have equal concentration of sodium and potassium, then we don't have energy, right? It's not a battery. So our goal is to make a battery. Our goal is to make it negative inside and positive outside, right? So, so far, there is no potential energy in this situation. It's not a battery because we don't have separation of charges. Same amount of sodium, potassium outside and inside. Well, what if we have a protein and it will be a pump, right? And this pump gonna always pump sodium out and potassium in. Look, and we do have this pump. Every single cell has this pump that is called sodium-potassium pump. So sodium constantly out, potassium in. Now here we have separation of not charges, right? But separation of ions. This is called chemical gradient, right? Now when sodium, we have high concentration of sodium outside and low concentration of sodium inside, we have concentration gradient for sodium. We have lots of potassium inside and very little outside. We have concentration gradient for potassium. This is called chemical gradient, and chemical gradient is achieved by sodium-potassium pump. And it uses energy, ATP energy to do it. So to remember it, just remember your cells are salty because salt has sodium, sodium chloride, salty bananas. And banana has high concentration of potassium. So your cells have lots of sodium outside and lots of potassium inside because of sodium-potassium pump. And this is called chemical gradient. Now look, what's gonna happen if you allow these particles to move, freely move through this membrane? If we make, opening inside this membrane, and we call this opening channels, right? If we have these leakage channels, then where would sodium go? Well, obviously sodium would go in, down its concentration gradient. Where would potassium go? Well, potassium would go out, down its concentration gradient, right? And then we would go back to this situation. But this is not a case because inside a membrane of a cell, we do have leakage channels for sodium and potassium, but we have way more channels for potassium. So we have very few for sodium. So only few sodium particles move in, but lots of potassium can move out, right? So now, just for purpose of understanding for a minute, imagine that we don't have any sodium channels that are open. We only have potassium. See, this shows only potassium channels. Now what's gonna happen if we allow potassium to move? Potassium will move out. Now, when potassium start moving out, potassium has positive charge. That makes sense? So now inside your cells, you have less and less and less positively charged particles. So you see your cells became negative inside. And this is electrical gradient. But because this electrical gradient is not possible without chemical gradient, together it's called electrochemical gradient. So cell slowly become more negative inside and more positive outside. But potassium doesn't reach its equilibrium. Why? Because potassium can move out and in. So potassium moving out because of the chemical gradient, but now some potassium start moving back in, right? Because if here we have negative charge inside and potassium is positively charged, then it will be attracted to a negative inferior of the cells. Interior, inside. So negative charge inside a cell, right? So again, potassium moves out because of the chemical gradient. And potassium moves in because of the electrical gradient. Potassium is attracted by this negatively charged proteins inside the cell. And at some point of time, it reaches equilibrium. The same amount of potassium moves out, the same amount of potassium moves in, and we're reaching minus 70 millivolts over here, right? So this part from here to here, this is how we establish this minus 70, right? That is the resting membrane potential, right? That makes sense? So again, If we have the same concentration of sodium, potassium inside and outside of the cell, no energy, right? 0 voltage. Now, if we start moving sodium out, potassium in, because of sodium potassium pump, we have chemical gradient, but we don't have electrical gradient yet. So we still have the same number of positive particle outside and the same number of positive particle inside. But when we open potassium leakage channels and potassium start moving out, cell became more and more and more negative. When cell inside became negative, it start attracting potassium back in. When this movement of potassium reaches its equilibrium, when chemical gradient equals electrical gradient, we establish this minus 70 resting membrane potential. That makes sense? So that's how minus 70 is achieved. Now in axons, remember we can make cell positive inside. How to do it? Well, we need to open another channels. To make cell positive inside, we need to bring positive charges in. So if sodium channels are open, some sodium gated channels are open, then sodium start moving in. And when positive particles moves in, cell became more and more and more positive inside, right? And if we have enough sodium moved in and we go from minus 70 to minus 55, then we have voltage gated sodium channel open. And the whole bunch of sodium moves in and cell became positive inside and it reaches plus 30, right? Then sodium channels closed. When sodium channels closed, voltage gated potassium channels open and potassium moving out, right? It's too positive inside. We need to go back to minus 70. So what we can do? Well, let the potassium move out. So potassium moved out through voltage gated potassium channels. Now we're losing positive particles. We became negative inside. So here's the negative inside. So we kind of good over here, we negative inside and positive outside, but look, now we have, okay, so this moved in. I don't like this picture very much. So if sodium moves in and potassium moves out, we have lots of sodium inside and lots of potassium outside. That's not a salty banana. Now we need sodium potassium pump to push sodium out, potassium in, to back to our normal resting stage, right? Does make sense? Well, we have way more slides to talk about it at the end. I hope this will make sense. Now, so here we have the overview. So resting membrane potential when neuron is polarized. So this picture show us RMP. Negative inside, neuron is negative inside, positive outside, and it's salty banana. Sodium concentration is high outside, potassium concentration is high inside, right? So this is resting membrane potential and cell is polarized. Neuron is polarized. Now, if we apply a stimulus, then sodium start moving in. Look, sodium start moving in. So inside we have more positive charges. So stimulus causes neuron to depolarize, became less negative. Now we need to reach a threshold. Enough sodium need to move in, right? So you see here we have enough sodium moved in, and if threshold is reached, then voltage gated sodium channels open and lots of sodium moves in. And this will be our action potential. So this is action potential, positive inside, negative outside. And action potential will actually move along this axon. So when a threshold, when a strong stimulus create action potential down the length of the axon. And then neuron repolarize. So in this area where we have action potential, now we go back to a normal state, negative inside, positive outside, because of the potassium moving out through the voltage gated potassium channel. And then we have sodium potassium pump that kind of make everything back to normal, pump sodium out, potassium in, so back to the resting stage. Well, sometimes what happen, neuron can, well, I think it happen all the time, neuron can hyperpolarize. So it's repolarized, so it became -70, and then more potassium moving out, so it became maybe -75, -80, so it became even more negative. And when neuron became more negative than -70, this is called hyperpolarization. And after hyperpolarization, we return back to resting potential. Okay, so here's resting membrane potential. This is a picture that represents resting membrane potential. Negative inside, positive outside, sodium outside, potassium inside. And in this point, what we have, sodium potassium pump is working, right? Sodium out, potassium in, and we do have some leakage channels. Potassium diffuses out, sodium diffuses in, but way, way less sodium diffuses in because very few channels are open. But potassium diffuses out really well, right? So here, this is what we have. Lots of sodium outside, right? Lots of potassium inside. This is our salty banana. This is our membrane. Now, where would be the favored direction of potassium diffusion? Of course, potassium wants to move down its concentration gradient. Potassium want to move out. Where would be the favored direction of sodium diffusion? Well, the sodium would love to move in, down its concentration gradient, right? But here's the problem. We have lots of potassium channels that are leakage channels and very, very few sodium. So we're losing these positive charges. And we're losing these positive charges, cell became negative, look over here, cell became negative inside and positive outside. Of course, some sodium did return, in, but because we have way more potassium leakage channels, cell reaches this -70 millivolt. And this is kind of equilibrium. This is equilibrium that is achieved by sodium-potassium pump and leakage channels. And that's what resting membrane potential is. So this is separation of charges. Your cell became little batteries. They do have potential energy. Right, so that's RMP, resting membrane potential. So here's our electrochemical gradient that was created. Electrochemical gradient is the sum of all electrical and chemical forces acting across the cell membrane. This is potential energy. Electrochemical gradient is due to concentration of charged particles, negatively proteins and potassium inside, and sodium and chloride outside. So let's look at this diagram very quickly. So this line represents cell membrane. Here's inside a cell, outside of the cell. So what do we have outside the cell? We have salt, right? That's why it is salty banana. So we have high sodium concentration, high chloride concentration, and very little potassium. Now what do we have inside? Inside we have potassium. Lots of potassium, and we have negatively charged proteins. We do have chloride ions inside as well, less than outside, and we have sodium very little inside, right? Sodium chloride outside, potassium and negatively charged proteins inside. Now, chloride can move in and out, so that's why this can be ignored because it can move down its concentration gradient. Proteins cannot leave the cell. Sodium, very little sodium can move, but potassium can move out. Lots of leakage potassium channels. So potassium can move out, right? Sodium cannot move in. So if potassium can move out, what do you think it's gonna do? It start moving out, right? From high concentration to low concentration. And this will create negative charge inside, right? But we're talking about electrochemical gradient. Let's start with the chemical gradient. So chemical gradient develops when there are more ions of a substance in one area than in another. So chemical gradients develop when we have a lot of sodium outside, little inside. So we have chemical gradient for sodium. Do we have chemical gradient for potassium? Yes, we have, because we have lots of potassium in, very little potassium out. So we have chemical gradient for potassium, and we have chemical gradient for sodium. Now, ions tends to move from area of high concentration to area of low concentration or down their concentration gradient. So sodium has tendency to move in, and potassium has tendency to move out. So that's a chemical gradient. Now, why do we have so much sodium outside? And why do we have so much potassium inside? Because of sodium-potassium pump. Because your cells, they're doing it. They pumping sodium out and they pumping potassium in. And they use lots of energy to do it. Now, electrical gradient develops when there are more positive or negative charges on one side of a membrane than on the other, right? So now if you look over here, do we have electrical gradient here or not? And when you, first you look over here, you think, I don't know, I have negative, positive, negative, positive, positive, negative, positive. It seems like I don't really have a separation of charges here, but you do. You do separation of charges here, and I'll show you why. Let me pick up the pen. Now look, because this cannot move, right? It cannot move out. So that's why we're gonna ignore this. We also gonna ignore chloride. We're gonna ignore it, right? Because chloride actually can move pretty well in and out. So everything that can move, you know, it doesn't affect our situations that much. Now look, because sodium cannot move in, right? So, well, very little can move. So let's just for a second think no sodium moving in, but potassium moving out. Now, when potassium starts moving out, right? So here's potassium. Here's potassium, right? Here's potassium. What now you tell me, do I have electrical gradient or not? Lots of potassium moved out, so I have plus, 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 and plus, right? What do I have inside? Oh, actually, you know what? Maybe I should not ignore this. Let me get my eraser. Sorry for that. And I will tell you why we should not ignore this one. I'll back to the pointer. We ignore chloride because chloride can move in and out, right? So that's, we can imagine, well, maybe it will reach its equilibrium. Enough chloride will move in. But those are proteins. So those are proteins inside a cell that have negative charge. So they stay inside the cell all the time, right? So now when potassium moving out, so we have plus, 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 and plus for sodium, right? And we have less and less pluses here because they're moving out, but we still have the same number of minuses. So we do have this separation of charges, pluses outside and minuses inside, right? That makes sense. So let's again grab a pen. So now this became actually smaller, right? So let's just kind of like, yeah, it's not there. However, we do have it inside, but just imagine that many, and now we have kind of like less potassium inside, and we have so many positive charges outside, few inside, but we have lots of negative charges still inside because those proteins cannot move out of the cell, right? So they stay in. Now here we have electrical gradient. I'm gonna repeat this one more time, right? So electrical gradient develops when there are more positive or negative charges. So we have more positive outside and less positive inside. And ions, of course, tends to move also from to the area of opposite charge. So this potassium will have tendency to move back in because it's negative charge inside. So the movement of potassium will reach equilibrium, and this equilibrium is at minus 70 millivolts, not at 0, right? Okay, so let's back over here. Here or over there. Yeah, so we will look at this picture again. So because of this sodium-potassium pump, there is separation of sodium and potassium. And this is our chemical gradient. Now, chemical gradient is not electrical gradient. It's not good enough for us to have this electrical impulse. But because inside the membrane, we have lots of potassium leakage channels or leak channels, now this potassium start diffusing out. When potassium diffusing out, the cell became negative inside and positive outside. And this is our electrochemical gradient now, because we have both chemical and electrical gradient. Right, so is it getting a little bit better? I hope so. So electrochemical gradient is established by sodium-potassium pump. So sodium-potassium pump works this way. When 1 ATP is used, 3 sodium moves out, 1, 2, 3, and 2 potassium moves in. 3 out, 2 in. So electrochemical gradient outside cell is positive, inside is negative. We already talked about it. So cell is negative inside, positive outside. Now, voltage gated channels, they all are closed, but we do have leak channels. So sodium and potassium start leaking. So your pump is working hard to separating sodium out, potassium in, but because of these leak channels, sodium, start moving in, potassium start moving out, but more potassium moving out, more potassium leak channels. Also, negatively charged proteins remained inside the cell. So which way potassium go? Well, potassium will go out of the cell, right? Which way sodium would go? Sodium will go inside the cell, from high concentration to low concentration. So sodium and potassium move down the concentration gradients. Sodium diffuses in and potassium out, but membrane is 75 times more permeable to potassium than sodium. So more potassium diffuses out than sodium diffuses in. And this increases the number of positive charges on the outside relative to inside. or here it says that sodium potassium pump carries 3 sodium out and only 2 potassium in, right? So we still, even pump itself, pumping more positive charges out. So it became more positive charges outside and less positive charges inside, right? And of course, negatively charged proteins stay inside the cytoplasm and make membrane negatively charged. So therefore, the inside of the membrane is measured as minus 70 millivolt. And this is called resting membrane potential, right? So that's where we finally, hopefully, we explain why cell is negative inside and positive outside, and it's measured minus 70 millivolts. Next step is depolarization. So cell is polarized. So this is resting membrane potential, cell is polarized. Now we're moving towards now positive. This is called depolarization. And depolarization happens when sodium moves inside. So positive sodium moves inside and cell became less and less negative, right? So this is depolarization. So here we will talk about depolarization. So sodium voltage gated channels open at a certain voltage and open for a set amount of time. After the set amount of time, they became inactive. And after a certain amount of time, they become closed again and can be stimulated to open again, right? So, so over here, in a depolarization, we will have sodium voltage gated channels that will be open and sodium start moving in. At a certain amount of time, they became inactive, right? And they became closed. And when they became closed, they can be reopened again. So here's depolarization. So which way does sodium go? Well, if we have lots of sodium outside, it would go inside, right? So over here, we have local potential that depolarizes axonema on a trigger zone. So look, over here, we write in the trigger zone, just the beginning of the axon. And so first we have this minus 70, right? So minus 70. But now imagine that we apply a stimulus, right? So over here, look, we apply a stimulus over here. We're stimulating this cell. So if we're stimulating this cell, sodium start moving in. You see sodium moving in. So positive particles are moving in. So cell became less negative. It moving towards minus 55. If enough sodium moved in and we reach this minus 55, this is called threshold. Now what's gonna happen? The voltage gated sodium channel will be open. Now, cell is negative inside here, positive outside. Voltage gated sodium channels are in a resting state. Voltage gated potassium channel in a resting state. And you see they closed in a resting state. Now, when this positive charge reaches this channel, it is voltage gated. So when voltage changes to minus 55, this channel opens and sodium rushes in. Look, lots of positive charges rushes in. So it's a very steep change in a voltage. So it's go from minus 55 to plus 30. And this is called depolarization. So sodium rushes into the cell, making inside more positive. So here's the sodium enters positive. Opening sodium channel allow positive charges to enter, therefore making inferior less negative from minus 70 to minus 60 to minus 55, right? And then when we open the voltage gated, the cell became positive inside, so plus 30. So once this depolarization has started, it can either die, or if the internal part of the cell memory reaches 55 millivolt, then it can reach threshold. It has reached threshold and action potential will happen. A threshold charge minus 55 millivolt causes neighboring sodium VGC, voltage gated channel, open. This depolarize the next part of the axon, and it continues down to the axon terminus, like you toppling the dominoes. If depolarization does not reach threshold, no action potential will happen. Let me get to the, let me get here. Yeah, let me see. Okay, so this cell in a resting membrane potential, right? So you apply the stimulus. And what is the stimulus? Stimulus is anything that open sodium channels. So sodium start moving in. So very little sodium moves in. Let me pick up the pen. So let's imagine that very little stimulus is applied. So sodium moves in, but not enough. So it can pretty much die like this, back to the resting. Or even if it goes a little bit more and it can die again. Only if it reaches minus 55. So enough sodium moves in, then voltage gated channels open and we go all the way to 30, right? So, so let me, okay, so here, for example, the neuron, right? And that's its axon. So here's the axon. So here's the nucleus, those are dendrites, right? So let's imagine that this cell, this neuron is located in your skin. And maybe it's located in the skin of your leg. So you outside camping, you sitting on your camp chair, right? And then maybe some bug, like ladybug. Ladybug is crawling on your leg. And you know, when ladybug, right? So let's imagine this is the ladybug, right? So here's the ladybug. I don't know, here's the, it's crawling on your leg, right? Now, ladybug putting some pressure, right, on your skin. It's very little pressure, but there is a pressure. So when ladybug pushes this pressure on your skin, what happened? Mechanically gated sodium channel open and sodium start moving in, right? So ladybug is crawling on your leg. It's pushing on your skin. It's pushing some pressure on your skin. And this actually activates this mechanically gated sodium channel. So sodium start moving in. But you know if it happened with you or not, but sometimes these little bugs are almost all the way up to your leg and you didn't feel it. Why? Because not enough sodium came in. So not enough sodium came in, you don't generate this action potential. So this impulse never reaches your brain. So you don't feel this ladybug. But if ladybug stays long enough on your skin and enough sodium moves in, then minus 70 became minus 55, right? And what happened, right? So what happened over here, voltage gated sodium channel. This is voltage gated. So the whole bunch of sodium now moves in. The whole bunch of sodium, so it's right here. All sodium moves in. And action potential is generated, so impulse reaches your brain, so you feel how this ladybug is crawling on your leg. That makes sense? So for you to feel anything, right? Or let's say somebody touching you very slightly. Sometimes they touch you, you don't feel it. But every time somebody touches you, what happened, the sodium channel open and a little sodium moves in, right? Is it enough sodium to move in to reach minus 55? If yes, then voltage gated sodium channel open. Many of them are open and sodium rushes in and then electrical impulse is generated and you will feel this sensation. And this is will called depolarization, right? And then, okay, where are we at? So depolarization, and then we need to repolarization. Okay, so that's our, so this is where we stop. One depolarization has started, it can die, right? So again, you might feel somebody touching you or you might not. If it's very, very slight touch, not enough sodium moves in, so this threshold is not reached, that's this local depolarization, it's died. But if the cell membrane reaches minus 55, it reaches threshold, then the action potential will happen, right? Let me pick up my pointer again. So threshold charge minus 55 causes neighboring sodium voltage gated channels open. And this brings so many sodium in, right? Then we have generation of action potential. And then this will continue along the axon all the way down to your central nervous system. So if depolarization does not reach threshold, no action potential will happen. So action potential operate in all or none principle. Stimulus has to open enough sodium voltage gated channels to reach threshold. If threshold is reached, we have action potential. If no threshold is reached, no action potential. So, but once this action potential has been generated, the amplitude of depolarization wave will be the same for all action potential generated. So action potential are never go higher or lower. It's always will be to plus 30 and then back. So let's look what's going on over here, right? So here we have local potential, right? So local potential, so enough sodium moves in, right? The cell is positive inside now and negative outside. Now this is voltage gated channels. So the voltage gated channels everywhere along after this local membrane over here, right? Where we create local potential, they all closed. They all closed. But if we reach this minus 55, right? If we reach minus 55, from minus 70 to minus 55, then the voltage gated sodium channel opens. So sodium rushes in, right? And the sodium diffuses along the axon and it opens next voltage gated sodium channel. And then it open next voltage gated. So this is VGC, sodium VGC. You see, it's open here, then it's open here, then open here, and this is our action potential that is moving toward your central nervous system. It can move away from your central nervous system as well. But, right, so here we have movement of electrical signal. Now here where we have this, we have resting membrane, depolarization, right, depolarization, and then before it, we have repolarization. So it's depolarized first, and then it's repolarized back. And it's depolarized and repolarized back, because we do need to go back to the resting membrane potential. So types of conduction. It can be normal unmyelinated axon. Then we need to open every single VGC, right, along the axon. So this will be normal conduction in unmyelinated axon. But if we have this myelin sheath, then VGC are only open at a node of Ranvier. And what it does, it increases the speed or velocity, speed of action potential. So actually electrical impulse is, it's moving very fast and it's jumping from one node to another node. And this is called saltatory conduction or saltatory propagation. So after depolarization, we need repolarization. So almost immediately after depolarization, sodium VGC became inactive. Now, so what happened over here, right? Remember, sodium moved in. We opened VGC for sodium, sodium moved in, and cell became positive inside. Now, how to return it back to negative? How can the inside become more negative? Well, potassium VGC open. When potassium VGC open, we have so much potassium inside, right? Potassium will go out. And when potassium will go out, we're losing positive charges. So what's gonna be with our voltage? It will go back to the negative, right? And so we go now from plus 30 back to minus 55 and minus 70. So potassium VGC remain open for a certain amount of time and then close. Now we're going, so over here, this is our, so remember, let's look over here. This is our resting membrane potential, right? So cell is polarized. This is depolarization. And now we in repolarization. So we want to everything back to minus 70. How to do it? We need to open potassium channels, voltage gated potassium channels. So potassium start moving out. When potassium moving out, cell became what? Less positive and more negative outside, inside, right? So we return back to negative inside and positive outside. And actually, this potassium VGC can open a little bit longer than they supposed to, and cell became even more negative inside. So it's not minus 70, it might be minus 72, minus 75, right? Minus 80, and this is called hyperpolarization. So axolema may hyperpolarize before potassium channel return to their resting state. So this hyperpolarization, to make inside excessively negative, this is what hyperpolarization is. So potassium VGC close at various times during hyperpolarization. The ones that open first, close first. The ones that opens later, close later. So potassium still rushing out and more potassium moving out. And that's why we have this excessively negative charge inside a cell. And then when all this done, sodium potassium pump brings membrane back to resting potential, and it's make the concentration of ions right. So it's pushing sodium out, potassium in. Now, what is refractory period? Refractory period where cells cannot be excited. We have absolute refractory period and relative refractory period. Let's look at this picture over here. So absolute refractory period, this when no stimulus can excite a cell. Even very strong stimulus cannot cause action potential. But let's look at the sodium voltage gated channels shown here in pink. They can be in resting state. So this is resting state, right? Here they are activated, so they can be open and they can be closed, right? This is again resting state. So resting state, open or activated, and closed or inactivated. So when sodium channels are either activated, right? Or when they are inactivated. This is absolute refractory period. Only when sodium channel back to a resting state, at least some of them, this will be our relative refractory period. So in this point of time, if stimulus is strong enough, we can generate action potential. Right, so let's read over here. Absolute refractory period, sodium VGC are inactive no matter how the voltage is. Ensure one-way propagation of charge. So sodium voltage-gated channels are inactive and nothing can excite a cell. Relative refractory period, some sodium VGC are now closed and some still inactive. And when they closed, right, they can be stimulated again. So look, so we have resting state again, we have activated, and we have inactivated. So we need this sodium channel, at least some of them, to return back to a resting state so we can activate them again. So absolute refractory period, no stimulus can generate action potential. Relative refractory period, strong stimulus can generate action potential. Let me see how many slides. Okay, well, actually, that's it for action potential. Now we're getting to synapse. Synapse is easier. So when action potential reaches the axon terminal, it must move to the next cell. Then calcium voltage-gated channels open, calcium will move in, and calcium will cause a synaptic vesicle to fuse and release neurotransmitters. So let's look at the picture over here. So here's our action potential coming to the axon terminal. Now, what is this action potential? Cell positive inside, negative outside. When this happens, it's reaching this calcium voltage-gated VGC channels. Calcium moves in. Calcium causes these synaptic vesicles to fuse with the membrane of presynaptic axon and release of neurotransmitter. So when neurotransmitter is released, neurotransmitter attaches to its receptor and it opens sodium channels again, and sodium start moving in. And now we have kind of propagation of the electrical signal from one neuron to another neuron, because we open the sodium channels again, so we can start all over, right? Enough sodium moves in. This membrane inside reaches -55, right? VGC, sodium channel open, sodium in, action potential, potassium out, sodium potassium pump, returns everything back to normal. Neurotransmitters can be excitatory or inhibitory. Acetylcholine, epinephrine, norepinephrine, histamine, glutamic acid, those are mostly excitatory neurotransmitters. Inhibitory will be serotonin, endorphins, dopamine, GABA, right? Acetylcholine for muscle movement, epinephrine, norepinephrine for wakefulness, arousal. Histamine promotes alertness. Glutamic acid, memory and learning. Serotonin, memory, emotion, sleep, temperature regulation. Endorphins reduce pain. Dopamine give you motivation, pleasure. GABA is regulation of excitability and muscle tone. So it's a very well-known inhibitory neurotransmitter. Right, and as the last slide just show you, you know, the structure of these neurotransmitters that you don't need to memorize. Okay, I know that was not an easy topic. So you guys, of course, wanna read your chapter. you want to watch this video, you want to maybe find some other video on YouTube, and please let me know if you have any questions. Thank you for watching, and I hope it was helpful.